So here is it. Here is your point. So you can think about it as point of the plane. Okay. So this is 3 plus 2i. So any complex number will represent a point of two-dimensional plane. There is another way of looking at it geometrically. You can think about 3 plus 2i. That's one way to look at it. The other way is think about this as a vector whose components are 2, 3, and 2. But again, you have to work in two-dimensional because it is a two-dimensional vector. So if you look at it this way, then here's what we have. Again, 3, 2. So you look at it as this vector, okay? Well, in either way, when you add the two complex numbers, you are adding the corresponding components, right? So what happens when we say, I am going to add 4 plus I and 2 plus 3i? Geometrically, this addition, if you look at it as a vector, this is what happens. 4 plus I is this one, looking at it as a vector. Then 2 and 3. This is the second one. Adding these two is like adding these two numbers. If you think about it as a vectors, it is adding these two vectors, and you know how to add these vectors. You simply go parallel to this and parallel to this one from here. You form this parallelogram, and the diagonal is the sum. Okay? So if this is the 1, this is the 2, this diagonal is the 1 plus z2. And of course, this one will be z1 minus z2. Okay. I just wanted to give you some geometric interpretation. Now, going to this version that we think about it as a point in the plane, an ordered pair. So you have A plus BI. You can think about it as ordered pair, which represents a point in the plane. Okay, here's the point in the plane. Here is A, here is B. Well, in planes, every point will have also polar representation. Um, Writing a polar representation of this one, so polar format. In polar format, remember, we are dealing with r and theta. What is r? R is the distance from this origin to the point. So this is r. What is theta? Theta is the angle made by positive direction of x-axis, measured counterclockwise. So this is theta. This is theta, okay? So in this triangle, A is r cosine theta, right? Just write the cosine of theta is adjacent divided by hypotenuse. So, and B is r sine theta. Now, if I put them together in a complex, as a complex number, A plus BI, it will be r cosine theta plus I, this. I'm going to factor that r. It will be cosine theta plus I sine theta. But there are some terms here. This r, which is the distance from the origin to the point, we can compute it, of course, right? From this triangle, right triangle, r is the square root of a squared plus b squared. So r squared is a squared plus b squared. Oh, remember this one, right? A squared plus b squared is, if I call this one, this number z, is the same as z bar. We call this one r, which is modulus of z squared, right? So, so that r, which is another notation for that r, is this modulus. We call this one modulus of z. Is the square root of real part plus imaginary. As I said, we call it modulus. This angle theta, we call it argument of z. Okay, call it argument z. The way to find it of course, from this triangle, you see tangent of theta is b over a, right? So tangent of theta, we usually don't put n there, right? Tangent theta is b over a. So theta is tangent inverse, but always plot the point to find that theta. This theta is called argument of z, okay? Argument of z. Well, there is a beautiful identity called Euler's. See, here is Euler identity. We can easily prove this, justify why that's the case. Euler's identity is this. The cosine theta plus I sine theta is e to the I theta. If I use this one in this format, say, in right here, in this parenthesis, e to the I theta, then I will get this z, which is a plus bi, is r. R is modulus of z, okay, e to the I theta. This is the same as r e to the I theta. Now, this formula has a lot of interesting application. So this is called polar representation of this complex number. So any complex number a plus bi has also, can be written, let's say, has a polar representation, but can also be written as its modulus times e to the I theta, right? Now, let's call this one polar format. Either this one or that, the previous one. Now, what is the advantage of having this polar format? There are a lot of advantages, all right. One of the advantages is this. So I'm just going to write Euler's identity, which is cosine theta plus I sine theta. If you raise both sides to, let's say, power 2, so cosine theta plus I sine theta squared is e to the 2 I theta. I'm going to expand this. On the left-hand side, you have cosine squared theta. Just multiply this out, all right? Plus 2i sine theta cosine theta. Then this is squared. This is squared, I squared is -1. On the other side, using the fact that e to the I theta is this, right? So now it is e to the I times 2 theta. So it will be cosine 2 theta plus I sine 2 theta. Okay, so in this formula, we have a complex number here on the right, a complex number on the left. The real part should be the same as the same, and the imaginary part should be the same. If two complex numbers are equal, that means they are identical, right? So the real part here is this one minus this one. So cosine squared theta minus sine squared theta. The real part in this part on the right-hand side is cosine of 2 theta. So cosine of 2 theta was written in terms of sine and cosine of theta. So this is double angle here, but it's a single angle here, right? The imaginary part should be the same. The imaginary part in this side is sine of 2 theta. On the left, the imaginary part is 2 sine theta cosine theta. So that gives me sine of 2 theta in terms of sine theta and cosine theta, right? It's a trig identity that you're familiar with. Now, of course, we can manipulate this and do better. For example, this is good. But this one we can manipulate. For example, I can write sine squared as 1 minus cosine squared, right? Because sine squared plus cosine squared is 1. So this one, I can write cosine squared theta. Instead of sine squared, I will write this. Cosine of 2 theta. So is cosine squared minus 1. So this tells me that cosine of 2 theta is 2 cosine squared theta minus 1. Oh, you have seen this one a lot, especially in integration. When you are integrating even powers of cosine, you want to change it to the double. So from this equation, we get cosine squared theta is 1 plus cosine of 2 theta divided by 2. Okay. Now, just giving you a very simple example that to remind you that you used this formula a lot. Here is how we take integral of cosine square. Instead of cosine square, I will put from this, I will reduce I will use this formula to reduce the power, get rid of a square. So here we get 1 plus cosine of 2x divided by 2. Oh, this 1/2 is, you can pull it out, right? So integrating, it is x over 2. Then integral of cosine sine. Sine of 2x plus a constant c. All right? So that is how you dealt with this formula. Of course, we can find a similar formula instead of writing in terms of cosine. We can write cosine to be 1 minus sine squared, and you will have 1 minus 2 sine squared. Theta is cosine 2 theta. And here, sine squared theta, or x, whatever, is 1 minus cosine 2 theta divided by 2. Again, you can use this in integrating the different powers of even powers of sine. Okay. Well, I just gave you one example, but the main thing was expressing sine of 2 theta and cosine of 2 theta in terms of sine of theta and cosine theta. You can do this. You can generalize this. You can go ahead. For example, if you raise to third power cosine, let's say x, plus I sine x to the third is e to the ix to the third, so I 3x or 3ix. Now, if you expand it, you get cosine q 3i cosine squared x sine x minus 3i cosine x sine squared minus I sine q. This is the left-hand side equals to cosine of 3x plus I, the right-hand side, all right? Sine of 3x. So again, let the real part be the same as real part, imaginary the same as real imaginary part. So cosine 3x will be the real part on the left, cosine q, and this one. I don't need this I here because it is I squared. and I squared becomes -1. -3 cosine x sine squared. Imaginary part will be the same, so sine of 3x is the same as imaginary part here, so it will be 3 cosine squared sine x minus sine cube. So we expressed cosine of 3x in terms of just cosine x and sine x. Here, in general, we can do with n, so cosine x plus I sine x to the n is e to the I nx, and e to the I nx, using Euler's, you will have cosine of nx plus I sine of. Okay. Well, I'll stop right here. I'm not quite done with section 13.2. I will continue section 13.2 also on Thursday. Hopefully on Thursday, I will complete section 13.2 and 13.3. Well, since you told me that there is a practice session on Fridays, I will change the spreadsheet and make sure that I will include that practice sheet. So, any comment, any question? Homework today is section 13.1, 3Ks. You can go ahead and read section 13.2 as well, and be proactive and do those problems 3Ks. But remember, when it says 3K, so here is section 13.1, 3K. It says 3K, all right? This 3K means do the problems 3, 6, 9, and so forth. Just multiples of 3. You can also go ahead and read section 13, although I'm not completely done, but you can read this. Here again, it says 3K, okay? Which means the same thing. Any other question? No question? All right. Have a good day, everybody. I will see you on Thursday right here.